So okay, yeah. So let's hope the recording is running. So welcome again. Chris already introduced me, so I'm Nico, and today I'm going to talk about the topic of quantum reinforcement learning, which has been my area of research for the past approximately 2 years. And what I'm mostly focusing on is quantum policy gradient methods, so we thought it would be a good fit at the current point in the lecture. So, and as always, if there are any questions in between, just feel free to interrupt me at any point. So yeah, to begin with, what today will be all about. So what we had so far in the lecture was classical reinforcement learning and deep reinforcement learning. So this classical interaction loop where you have the environment, your agent, and you can represent your policy, for example, with a deep neural network. So that's what we have done so far, so the typical reinforcement learning pipeline. And then the other field we will need for today is quantum computing. So here we actually have a picture of the quantum computer by IBM, which is standing in Ehningen in Baden-Württemberg. And so what quantum reinforcement learning does, it tries to combine those two fields of research to form quantum reinforcement learning. And so there's no unique definition on QAL or quantum reinforcement learning, but what we are going to interpret today is that we take some classical reinforcement learning approaches and try to enhance them with concepts from quantum computing to either, for example, enhance the parameter complexity or also enhance the sample complexity, so the number of interactions that we require with the environment. And so overall, quantum computing is some a computing paradigm that's completely different from classical computing. I also will provide you with a short introduction to that. But yeah, that's for now. And some more motivational slides. So first of all, I think you all have heard of quantum computing because it's a big topic in the news in the last few years. And it almost sounds a bit like science fiction to some extent. But I can tell you that it's not, because actually we really have, not we, but some people have really built some quantum computers we actually can use. And so, for example, IBM also provides public access to them. So if you're interested in the topic and want to play around with it a little bit, you also can just click on the link, and you actually can test some of their smaller quantum systems. And here again, that's just a picture of the quantum device we are currently working with, which is in the Ehninger lab, also built and provided by IBM. And so, because there are so many basically big promises of quantum computing, a lot of development and also a lot of money is currently being pumped into the development of new quantum hardware, but also new quantum software. So that's the basically current stand of where we are at quantum computing. And the reason why many people and also many research labs are interested in it is that it has many big promises in a lot of research areas. So first, to make one thing clear, quantum computing is not a general purpose computer like your classical device. So I think it's very unlikely that at some point we will play some computer games on it or use Excel. So that's not going to happen probably, but it's a really special purpose device. So for some very specific applications, you can get and speed up compared to classical devices, but for most typical all-day problems, we probably will still go on to use the classical approaches. And so there are several areas, so this is there are even more, but I think the most well-known also in the news is cryptography. So there's this famous Shor's algorithm, which once we have big enough and error-corrected quantum computers will break mostly all today available crypto systems, so everything based on RSA cipher or also in discrete logarithm. So basically almost everything that's used in the internet could be broken with quantum computers. So people are currently also developing post-quantum cryptography. which tries to deal with that. And also it offers great prospects for simulation, for example. If you, for example, talk about medicine development, you have to simulate some molecules and atoms, and those molecules are typically follow the rules of quantum mechanics, so it just makes sense to use a quantum computer to simulate that instead of a classical computer, which is usually not really feasible for larger simulations. And there are also some prospects for optimization, and also what we're going to talk about today for machine learning. So currently, I mean, for a lot of problems, neural networks are a good fit. For example, ChatGPT really surprised the world with what it can do already nowadays. But one big problem of these systems is that they really have a large scale, so you have billions of parameters, and training is also very expensive and time consuming. And so quantum computing offers one way to at least get around this bottleneck of training neural models to some extent. But there's also a downside because we are really in the early stages of quantum computing development. So all the systems we have access to nowadays are very small and are heavily affected by errors. So the things we really can do are quite limited nowadays. But if you just look back at the development stages of classical computers in the 60s, 70s, 80s, also nobody had thought about what you could do with them today. So I think still basically the prospects are very great. So then just a short overview of what I'm going to talk about today. So first of all, I'm giving a small, short introduction to quantum computing. I hope I didn't do too theoretical. Then I will just do a short recap of policy-based methods, so only the standard ones, and about the advanced methods I will talk a little bit more on in the exercise on Friday. And then I will introduce some concrete algorithms from quantum computing, which we are currently working on. So, but to begin with, I actually want to show you a short YouTube video from Kurzgesagt, who I think do a very great job in explaining what quantum computing is all about. I just have tried to start it. Okay, just give me a second.
A computer is made up of very simple components doing very simple things, representing data, the means of processing it, and control mechanisms. Computer chips contain modules, which contain logic gates, which contain transistors. A transistor is the simplest form of a data processor in computers, basically a switch that can either block or open the way for information coming through. This information is made up of bits, which can be set to either 0 or 1. Combinations of several bits are used to represent more complex information. Transistors are combined to create logic gates, which still do very simple stuff. For example, an AND gate sends an output of 1 if all of its inputs are 1, and an output of 0 otherwise. Combinations of logic gates finally form meaningful modules, say for adding two numbers. Once you can add, you can also multiply, and once you can multiply, you can basically do anything. Since all basic operations are literally simpler than first-grade math, you can imagine a computer as a group of 7-year-olds answering really basic math questions. A large enough bunch of them could compute anything from astrophysics to Zelda. However, with parts getting tinier and tinier, quantum physics are making things tricky. In a nutshell, a transistor is just an electric switch. Electricity is electrons moving from one place to another, so a switch is a passage that can block electrons from moving in one direction. Today, a typical scale for transistors is 14 nanometers, which is about 8 times less than the HIV virus's diameter and 500 times smaller than a red blood cell's. As transistors are shrinking to the size of only a few atoms, electrons may just transfer themselves to the other side of a blocked passage via a process called quantum tunneling. In the quantum realm, physics works quite differently from the predictable ways we're used to, and traditional computers just stop making sense. We are approaching a real physical barrier for our technological progress. To solve this problem, scientists are trying to use these unusual quantum properties to their advantage by building quantum computers. In normal computers, bits are the smallest units of information. Quantum computers use qubits, which can also be set to one of two values. A qubit can be any two-level quantum system, such as a spin in a magnetic field or a single photon. 0 and 1 are this system's possible states, like the photon's horizontal or vertical polarization. In the quantum world, the qubit doesn't have to be in just one of those, it can be in any proportions of both states at once. This is called superposition. But as soon as you test its value, say by sending the photon through a filter, it has to decide to be either vertically or horizontally polarized. So as long as it's unobserved, the qubit is in a superposition of probabilities for 0 and 1, and you can't predict which it will be. But the instant you measure it, it collapses into one of the definite states. Superposition is a game changer. 4 classical bits can be in one of 2 to the power of 4 different configurations at a time. That's 16 possible combinations, out of which you can use just one. 4 qubits in superposition, however, can be in all of those 16 combinations at once. This number grows exponentially with each extra qubit. 20 of them can already store 1,000,000 values in parallel. A really weird and unintuitive property qubits can have is entanglement, a close connection that makes each of the qubits react to a change in the other's state instantaneously, no matter how far they are apart. This means that when measuring just one entangled qubit, you can directly deduce properties of its partners without having to look. Qubit manipulation is a mind-bender as well. A normal logic gate gets a simple set of inputs and produces one definite output. A quantum gate manipulates an input of superpositions, rotates probabilities, and produces another superposition as its output. So a quantum computer sets up some qubits, applies quantum gates to entangle them and manipulate probabilities, and finally measures the outcome, collapsing superpositions to an actual sequence of zeros and ones. What this means is that you get the entire lot of calculations that are possible with your setup all done at the same time. Ultimately, you can only measure one of the results, and it will only probably be the one you want, so you may have to double-check and try again. But by cleverly exploiting superposition and entanglement, this can be exponentially more efficient than would ever be possible on a normal computer.
Yeah, so much for that. So if you're more interested in the topic, I can really recommend this video. They're also talking about what quantum computing could be applied to. So if you're interested, just take another look. But for now, they already basically mentioned most of the important building blocks of quantum computing. And so the nice thing about really at least basic quantum computing is that you don't really need to be a quantum physicist to do it, but it's enough if you basically have a rough understanding of linear algebra. And I will just do what they told in the video, a bit more formal, but also not go into too much detail there. So, I mean, you probably all know that for classical computers, the basic unit of information is ones and zeros, so 1 bit. And for quantum computers, the corresponding unit is qubits, so basically the 0 state and the 1 state. And we also can associate this with those column vectors there. We will see shortly why we will do that, or why we want to do that. And then basically the probably most important property of qubits compared to classical bits is superposition. So classical bit can only be either 0 or 1, but in quantum computing we can be basically in all states in between. So basically we have a continuous set of states, and for that we have just some free factors of our basis states, so this basically coefficients alpha and beta, and now we can just use basically this convenient column vector notation to basically describe the state. And so alpha beta can just be any complex number. And so the important part here is that the absolute value squared of those amplitudes always has add up to 1. And that's basically down to the measurement, because if we measure our quantum state, basically the underlying wave function collapses and we will only measure one of the basis states. And so probability of measuring either of those basis states always has to be 1. So basically you always have this normalization condition here. And for a single qubit that's interesting, but actually not too powerful. But where things get interesting is if you look at larger systems, so basically at combinations of n qubits, because for that we do not only have 2, but we do have 2 to the power of n coefficients, or to the power of n amplitudes. So we have those basically n, also exponential magnitude to the power of n basis states, and each of the basis states has an associated amplitude. Those amplitudes are again just complex numbers, and so we also have to satisfy this normalization condition. So again, the absolute value squared of all these amplitudes has to sum up to 1. And this condition will get very important later on for the policy gradient algorithm we can design from that. So just keep that in mind. And now the next statement is a bit simplified, but what you usually also read in the news is that quantum computers are so powerful because you can do an exponential number of computation at once. And yeah, this is true to some parts, because we basically can process all of this 2 to the power of n complex amplitudes we have here in one go. So really basically have this somewhat exponential speed up, but you have to be careful with that, because the problem is that we cannot observe the quantum states. So in the end, to get some information about our system, we have to measure it. And as I already told in the video, if we measure the system, the quantum state collapses and we will only get one of the outputs. So we will basically measure one of the basis states that was in the full quantum state. And this makes things a bit more complicated. So because as soon as we measure, we basically destroy the superposition and only measure one of the basis states. And this measurement is inherently random. So that's just, at least following current physics, we believe that we basically cannot predict what the measurement outcome will be. Doesn't matter how much we know about our system. The only thing we know are the probabilities. So we know that basically the system will collapse to the basis state I with the associated absolute squared amplitude. And that's also the reason why basically all those amplitudes must sum to 1, because basically they just form a probability distribution over the entire space of basis states. And that's the only thing we know. And so you basically have to design your algorithm to make use of the superposition, also the entanglement that will be mentioned, and some kind of either positive or negative interference to basically boost the probabilities of the states that you want to measure in the end. Because again, the measurement is just completely random. You can't control which of the states you measure. And so if you basically want to reconstruct the full quantum state, you again would need an exponential amount of measurements, which would eliminate any advantage you can potentially get. So it's really not that trivial to design algorithms for quantum computers. And then for computing, it's always also important to be able to do state manipulation. And I mean, for classical computing, it's very simple. And so in principle, it's also very similar for quantum computing. So we can, for example, define this X operator here, which is basically just a not operator. And if we say we start in the all zero state, so for simple quantum systems, we can represent this as basically on this Bloch sphere here. And if you start there and just apply a NOT gate, then you basically just flip to the downward state, which is the one state. And the nice thing is that basically everything is linear, so it also automatically functions for all the superpositions in between. So that are the basic working principles. And now just my laptop hung itself, just a second. No. Okay, give me just a second and I will just restart it again. Okay. Perfect, should work again now. So Yeah, I will just go over that very briefly. So what we basically, how we basically typically describe our quantum algorithms are those quantum circuits. And this is just a very simple example where we basically can create a maximum entangled state. We will soon see what this means. And yeah, basically all quantum evaluations are just linear algebra. So we start in basically the all zero state, which we can denote by this column vector here. Then we apply a Hadamard gate, which is just this matrix, to the first qubit, and we apply just the identity gate to the second qubit. And yeah, again, that's just linear algebra, so you can easily compute that. And then the controlled NOT gate, so basically this gate here, can just be described by this matrix, and again the same, just computed. And so this will be the state you have finally prepared. And so this state is now maximally entangled because as soon as you measure the first qubit, you immediately know the properties of the second qubit. So we can measure the state and basically a probability of 1 over square root of 2 squared, so probability of 1/2, we will measure either the state 0, 0, or we will measure the state 1, 1. So we will never measure state 0, 1 or 1, 0. And that's why it's maximally entangled, so it's basically enough to just observe the first qubit. And if you know the first qubit is 0, then we immediately know the second qubit will also be 0, and the same for 1. But basically before we measure any of the qubits, both possibilities are there. So it can either be 0, 0 or 1, 1. And so that's the basic property of entanglement. And that's also basically one of the key ingredients we use in quantum computing, because this allows us to do operations not only locally on one qubit, but do operations simultaneously on entire subsystems of the qubits. Then again, some positive and negative points. So basically we already saw this in the beginning. There are some great prospects. So this is basically a circuit representation of a routine you need for Shor's algorithm, which will break crypto systems. And yeah, again, some other areas of application. And today we are going to look at the machine learning part. So those are basically the promises of quantum computing. But there are also some downsides, at least currently, because we are in something called the noisy intermediate scale quantum computing era, which just means that all quantum systems we have access to are very small and also affected by error very much. And so there are basically two main obstacles. The first one is that the quantum systems are just very unstable, because we're really talking, for example, about single electrons here, and controlling those electrons is not a trivial task. So we need some error correction routines for that, and there's actually a big bunch of theory on error correction, but it's still very difficult to really implement it in hardware. And then the second part is really an engineering question. So the biggest functional quantum computer currently by IBM has about 400 qubits. And so at some point things get very difficult to scale any further, because really for each basic qubit you need some control electronics, you need some wires, you need some way to basically model your microwave pulses. So this is really some engineering problem, how we really can just physically fit all of this control electronics onto a very small area. So those are I would say, two main problems that have to be solved for quantum computing to be really relevant in our everyday life, more or less. And then on towards quantum reinforcement learning. So the idea here is that we don't use this basically full-blown quantum algorithms, but we use variational quantum circuits instead. And those, I think, can somewhat be compared to classical neural networks, in that we also have 3 parameters in them. So we typically have a 3-layer structure. In the first layer, we encode our states, so basically the observation we get from our environment into some quantum state. So this is something like the input layer of a neural network. Then in the middle, we have the basically learnable blocks, where we just have 3 parameters. So for example, rotation angles of our qubits that we can adjust. And those correspond to the weights of a neural network. And we also usually use some entanglement gates to just basically be able to access a large room of this big Hilbert space and to make our model expressive. And then finally, because we can't directly observe quantum states, we have to perform some measurement to, for example, enable our agent to decide for an action, and also for computing gradients, as we will see later, to update our parameters. So those are the the 3 steps we always need for this variational quantum algorithms. And so the general pipeline will be that we just take our classical algorithm where we have this environment and agent interaction loop. And usually we use, for example, a neural network, a deep neural network, for approximating the policy or the value function. And now we want to replace this with a variational quantum circuit and approximate our policy with that. And so the idea and a bit the hope behind this is that those quantum circuits somewhat represent a more expressive class of function approximators, just because the basically Hilbert space, if you have access to them, is just much bigger than for classical neural networks. So we hope that we just can approximate a wider range of functions, and in the optimal case do this with much fewer parameters. So we hope that those models are easier to train, and then for very specific problems we actually can show that we can get a reduction in sampling complexity, sometimes even an exponential reduction. So we basically can dramatically reduce the number of interactions we need with our environments, and especially for some real-world applications where you really have, for example, to run some machines to acquire your data. This is a very important aspect. And the last point basically, which is not too important for us today, is that you also can directly work on quantum data. So for example, learning properties of molecules, which is very difficult to do with classical neural networks, because you have to first find some classical description of your quantum state and then learn on this one. But if you're able to use quantum networks, you can more or less directly upload the state of your molecule to your quantum circuit, and this makes things much easier. And then the second point is why a lot of people currently focus on this type of variational algorithms is that they typically need much fewer qubits than these big algorithms, and so we can really run them, at least for small examples, on current day hardware. And they also are believed to deal with the noise a little bit, because as we adjust the parameters, it makes sense that we also somewhat intrinsically are able to deal with the noise a bit better than with some fixed architecture. And how this concretely works, we will see in the third part. And now just a short overview of what there is in quantum reinforcement learning. So on the left side of the matrix, you basically have some algorithms that are just inspired by quantum computing, and we believe that they don't offer any intrinsic advantage compared to classical computing, so they are not too interesting probably. And then on the right side, here we have a lot of algorithms that are interesting and probably also very relevant, but they also require this big fault-tolerant quantum computers, which we just don't have, and we don't know when they will be available. Probably will still take some decades for that. But here you really can get some provable advantages, for example, in sampling complexity. So those are very interesting, but just not really doable yet. So what we currently focus on are this in-between algorithms, where we can do things actually on hardware, but typically we don't have any, or at least fewer, guarantees for the performance of our algorithms. But that's also very similar to deep learning. So for most deep learning algorithms, we don't really have guaranteed that there is a good performance, but if it works empirically well, you're basically happy. And today, we are looking at a very specific algorithm which tries to approximate the policy with a variational quantum circuit. So much on the introduction to quantum computing and quantum reinforcement learning. And now I'll just do a very brief recap of what is relevant from the lecture on policy-based reinforcement learning. So nothing too deep here. And so again, just the overview slide. So initially we started with value function approximation, but what you did in the last probably 2 lectures was a direct policy approximation, and that's also what we are going to focus on today. So for value function approximation, things were a bit different. So you approximate the value function and then typically selected the action that corresponded to the maximum Q value. So this was more like a deterministic policy. If you introduced the absolute greedy action selection, you had some stochastic elements in there, but still mostly deterministic. And what policy learning does instead, it usually uses this stochastic policies, which are directly described by a probability distribution. And so some environments, or actually many environments, the optimal policy is actually stochastic. So for those environments, policy learning is usually a very good fit. Then how do we actually train this algorithms? The basically typically go-to method is just to do gradient ascent. So we again want to maximize this expected reward of our policy, and assume that you basically are able to compute the gradient of this objective, which for classical neural networks is typically possible with backpropagation. How we can do that for quantum circuits we will see a bit later. But basically, as soon as we have the gradient, we can just use some gradient ascent methods. Compute this, we also call this typically policy gradient, and then basically just update our parameters in the direction of the gradient. So that's the idea there. Typically we have to use partial derivatives for that, but that's some technicalities in there. We also have some hyperparameters we have to set, so typically some learning rate, and obviously we also can do this with more advanced optimizers like ATOM or AMS-RAD or whatever. But that's the typical idea, so we can use the gradients to update our parameters. And from that, we basically need some way to actually estimate our gradients, because we are still in the model-free setting, so we don't have access to our environment dynamics, don't have a model of the environment. So we want to estimate this gradient solely based on the experience, so basically the interaction between agent and environment. So we can do some reinformation here. Details are not too important for now, so what's very important is that we basically can get rid of this environment dynamics here, and basically approximate this expectation value just by some finite number of interactions with the environment. So basically we need this log policy of our log gradient of our policy. So again, this just, for example, use backpropagation for that. And that's also something, so basically this cumulative reward is also something we can just compute based on the experience our agent has made. And so the intuition behind those kinds of algorithms is that we want to increase the probability of taking a path that just produces a high reward. So basically, if you use this notation here, a positive G, and in the other side, basically decrease the probability of producing trajectories with a low cumulative reward. So that's the intuition behind it. And so basically the first algorithm you always start with is this vanilla policy gradient or a reinforce algorithm in the here Monte Carlo formulation. So we basically sample several trajectories following our current policy. Then we can compute our cumulative returns. We can compute the gradients of our policy, and then just perform the gradient ascent steps. So that's the general algorithm, and that's also actually the algorithm where we'll start with for the quantum policy gradient algorithm. And then just another recap, because we also worked on this, but the theory behind it is also not too important for today. So this natural gradient idea, you also saw this in a lecture, so also we'll only go briefly over it. So what we did so far, we used basically just first order gradients to navigate in our parameter landscape. And the problem is a bit that those gradients are very closely tied to the Euclidean geometry, so we basically assume a flat landscape for this. But this is mostly or typically not the case. And so it might be that if we just do a small change in our parameter landscape, we actually might have a big change in our policy landscape. And this makes training usually very unstable. What we essentially do, we basically just do first order gradients in basically this neighborhood here, which is described again by Euclidean geometry. And what we instead want to do is basically perform optimization in the neighborhood that basically better captures the geometry of our actual landscape. And for that, we can use some second order terms, for example, based on the Fisher information matrix, based on the KL divergence. So the intuition behind it is just that we don't assume a flat landscape, but we actually capture the geometry of our landscape much better, and thereby are able to just perform much more targeted updates. And so in the lecture, I think you introduce all of the trust region policy optimization algorithm, and then one step further the PPO algorithm. But those are not too important for today, so we will just go with this basic natural gradient idea. Okay, so much on that. Now for the concrete algorithm. So in principle, we still have this typical interaction pipeline we already have seen several times. So we have our environment. In principle, we could also go for some environment based on quantum data here, but to keep things single for today, we can just use classical environment. We will use, for example, card poll later on. And then on the other side, we have our agent. And in this case, it's not a completely classical agent anymore, but it's basically a hybrid classical quantum agent. And so the part where the quantum comes in is the approximation of our policy. So we can encode our environment state into the policy, then perform basically have some free parameters there, prepare some quantum state, measure the state, and based on that we for one can represent our policy. And with a slightly adjusted circuit, we are also able to compute gradients of our parameters. So that's the part where we use basically the quantum neural network, and everything else still happens on the classical hardware. So we have basically our parameters stored classically, and as we are able to basically get the policy and the gradients directly from our network, we also can perform the updates classically. So we basically can still go with the same update routine, so with some gradient ascent based technique to just update our parameters. So we basically have the cyclic interaction between our quantum device and our classical device, where we update the parameters classically, then upload them to the quantum device again, do our new basically computations of policy and gradients, and basically do this hopefully till convergence. So that's the underlying idea. And a bit more formal, we again have this stochastic parameterized policy, only that this time we don't use a neural network but a quantum circuit to approximate it. And we still can use gradient ascent and can rely on the policy gradient theorem to sample our gradients. We only need a slightly different routine for getting an estimation and approximation of our gradients, but we will also see that later. And so what we basically just summarize what we do, we use our original reinforcement learning pipeline where we have neural networks as function approximators, and just and replace them with some variational quantum circuit which has basically two inputs. One is basically the environment state of our reinforcement learning environment, and the second one are the parameters we want to learn. So that's our general pipeline. And now we will go through the 3 steps you need. So first of all, we need to be able to encode our states. Then we need to update our parameters. For that we have need to have some routine to sample our gradients. And last but not least, we need to perform some measurements to, for example, decide for an action. So those are 2 steps, and let's start with the first one. So the encoding is actually a very non-trivial part, because it depends a lot on your concrete environment how you can do that. But I think that's also the case for classically, so not too much different there. I will go through some of the most prominent examples. So I think the simplest case is if you have some environment where you just have a discrete state set. So for example, this typical frozen lake environment where we just have 16 discrete states. And in this case, we can just use computational encoding for that, which means that in the first step, hang again, great. Sorry for that. So, where was I? So let's go again. Okay, now my pointer also works. So we have basically this environment here, and just assume we are just in the state number 11, and now we basically want to encode this into our quantum network. So for this, the first thing is we can just basically use a binary representation of the state, which just will be 1, 0, 1, 1. And then one thing we can do is we just can multiply everything by pi. We will see soon why we do that. And then we can just use this network on the right side to encode this into quantum states. So we basically just use basically every dimension, or basically every bit, we just encode into 1 qubit. And for that we can just use this rotations about the x and the z axis. And we actually also can visualize this very nicely on the Bloch sphere. So initially every qubit starts in a 0 state, and now if we apply a rotation about the basically x-axis by a value of pi, we just flip everything to the 1 state. And this is basically what we originally intended. So we basically want to encode this once here as the 1 quantum state. And then, so the packing part is optional. We also can use this additional RZ rotation. The reason for that is that we also have some global phases here. So if we do the Rx rotation, we basically introduce this global phase factor of -I. It's not too important for today what that is, and in principle it's also not relevant, because this global phase is something that doesn't matter for this algorithm, but in some other cases it might. So typically you want to remove this global phase, and to remove this global phase we can just apply another rotation about the z-axis, and then we basically get rid of this global phase and just have encoded basically the things in the 1 state. And yeah, on the other hand, if you just use basically parameter 0, then we don't apply any rotation at all and stay in the 0 state. So what we basically did here, we started with the classical state 1, 0, 1, 1 and encoded it into the quantum state 1, 0, 1, 1. So at this point, basically our network knows what is the current state in our reinforcement learning environment. And yeah, so this actually works quite nicely for environments where we have yeah, a discrete state set, and also actually, at least in theory, works for quite big environments, because we have this exponential growth in number of states we can represent. But typically this is not the most sophisticated encoding, so usually there are some better ones, but it's very simple. So that's the reason why a lot of people use it. But there are also some other environments where this doesn't really work out. because, for example, assume again the carpet environment, and here we have four states which all can take continuous values. And here it's not that simple to use this computational encoding. So in principle, we could say we discretize our state space and then still do this computational encoding. This might work, but then we again always have this additional overhead of deciding for a good discretization. And yeah, typically this is not the best way to do it. So there are also other ways or other routines to encode continuous states. And one way is this angle encoding. So we again just start with our four-dimensional state, so position, the velocity, the angle of the pole, and its angular velocity. And then the first thing is we have to scale basically all the values to the range of 0 to pi. So we still have to do some renormalization there, but this usually can be done. And the reason for that is that we now want to use rotation gates to encode the individual states. And so you also can just imagine it on a typical circle. If we start basically here, we rotate by pi, and then we rotate by 2 pi, and we're at the starting point again. So basically a rotation by pi or rotation by 3 pi produces the same state. And if we would do that, then we just would use the information and would lose the information. So basically to prevent this loss of information, we have to make sure that all states will be in the range 0 to 2 pi. And once we did this normalization, we can just use basically any set of rotation gates to encode the information by just using basically this as the angle. And in this case here we use Y and Z rotations and also some additional scaling parameters which are actually learnable, but those just increase the expressivity of our model. The important part is that we can just use basically this renormalized state values as the angles of our rotation gates, and by that also basically get a unique encoding of our RL environment state into some quantum state. So that's I think the encoding that is used for most of current algorithms, but there are also a lot of different encodings. So for example, you can talk about amplitude encoding, where you can encode the information directly into the amplitude of your system. This has the advantage that typically it requires exponentially less qubits to do this because it's very efficient, because you have this exponential number of amplitudes. But the big downside is that usually this encoding cannot be done efficiently. So you might need a huge number of gates to really do this encoding. And this is just something that's not feasible for current day hardware. So might be possible for some specific problems, but for a general problem it's just cannot be done efficiently. And then last but not least, there are also some routines which try to directly learn the encoding. And I think that makes a lot of sense because, I mean, all these three other encodings encode the information into the quantum system, but we don't really know if if the quantum state really captures the important information about our state. And if we directly train our encoding towards a different objective, for example, just optimizing some classification performance or some reword in a reinforcement learning setting, then we basically can make sure that we use basically all the important information in our RL state. But obviously the downside to this is that typically this is requires much more work because you have to retrain a lot. And so it would be nice to actually do that, but in practice it's usually also not very feasible. So the loss is just a broad overview of what you can do there, and for the examples we will see later we will actually go with this angle encoding, because it's just a good balance between being very simple to realize and still capturing a lot of the information of our state. So that's the first part of our relational quantum circuit. Then in the next part we have those learnable parameters, so for example angles of single qubit rotations here. And then at the end we will measure some expectation value, some observable, which will just collapse our quantum state. And this is actually somewhat a problem, because this prevents us from directly computing gradients. So if you go back to neural networks, computing gradients is actually pretty simple, so we can just use this backpropagation rule to get the gradients. But that is not possible here, because as soon as we perform the measurement, we basically lose most of the information about our system, so there's just no way to backpropagate. That just doesn't work out. We have to use different methods for that. And actually the method that's most commonly used is the so-called parameter shift rule, which is basically a specific instance of a finite differences approach. So we just take our parameters, vary them slightly in basically the positive and the negative direction, measure the same observable at the end, and then basically from the results we get, we can approximate the gradients of our with respect to our parameters. So this in principle works. Problem is a bit here that you introduce a large overhead, because we have to really sample a lot of quantum circuits to be able to approximate this gradient, because also again this is random measurement part. And there are some workaround for that, which makes things a bit more efficient, but for today basically that's the basic routine which we want to rely on. So yeah, just as a short repetition, we can't use backpropagation because we lose information once we measure, but we need to measure to get information basically for our agent. So what we do instead, we basically slightly vary our quantum circuits, and by that are able to approximate the gradients. And with these gradients, then we are able to perform gradient ascent, or basically any gradient-based technique like we would do for any classical algorithm. And then the last part, probably the also most important part, at some point we need to measure the quantum state, because we, for example, our agent needs to decide for a certain action based on the state. And for that, I mean, there's just no way around measuring it. And from a theoretical point of view, you typically measure some observables, some Hermitian matrices basically, and then we observe one of the eigenvalues and state collapses to one of the eigenstates. Details are again not too important. What we do in principle, what we basically do for all examples today, we measure in the computational basis. This just means that our quantum state collapses to one of the computational basis states. So basically, again, those are the computational basis states from which we originally constructed our quantum circuit. And if you measure in this basis, we are always guaranteed to observe one of the states. And if we do that, we can directly define this, this policy here. I will explain the concrete notation later. But what it basically does, it just measures our quantum system and then associates every potential basis state with one of the actions. So we can say if we measure the basis state, for example, 1, 0, 1, we decide for action 1. Just one example. And so that's very, very intuitive, I think. And for that, it's also very, very simple to compute the gradient. So basically, you can just use a chain rule for this logarithm here, and can then just use the parameter shift rule to compute or to estimate the gradients of this expectation value here. There are also some more complex gradient formulations where you use basically arbitrary observables. But here the downside is that you need to do some renormalization. So basically this is just another softmax function, so it's also called softmax policy. And this makes things a lot more difficult because you really need to measure the quantum circuits several times to really get access to this expectation values here. And for this example, as we will see in some slides, it's really enough to just measure the quantum circuit once to, for example, decide for an action, and that's really a big advantage. So we will stay with this simple definition for today. And Then, so the authors who proposed this approach actually also did some experiments. I think it was already 3 years ago, something like that. So they did everything in simulation. So basically, they simulated the quantum states and didn't do any experiments on quantum hardware. So just keep that in mind. And so they did some experiments, for example, on the cardboard environment with both the raw and the softmax policy. And they demonstrated that for basically both policies, you can get very close to optimal behavior. And we actually improved upon this algorithm. And if you do some improvements, you actually can perfectly learn the optimal policy. So here's just some, not really bugs, but some small, not perfect things in the algorithm. And then they also did actually some experiments on on an artificial constructed environment, which actually was sampled from some quantum data. And here they were able to show that you can do better with a quantum approach than with a classical approach. So red is basically just some typical classical neural network, and green is the quantum network. And so here we really have some separation between classical and quantum agent. So we can assume that for some problems, actually, quantum machine learning or quantum reinforcement learning is better suited than classical reinforcement learning. Of course, this is only empirical, so might be that there is some better classical network which is also able to learn it. So these results are interesting, but not too general. And so the same holds for this overall comparison. Yeah. So they did this to some extent. So I mean, already for this small example, I think the quantum circuit uses something like 30 to 40 parameters, and the neural network 600, 700. And they also increased this to several thousands, and they still weren't able to learn the optimal behavior. But I mean, things are also down to the structure of the network. So maybe if you just use a different neural network, maybe you can get to the optimal behavior. But that's something they didn't look into too deep. But yeah, I'm probably sure that for this simple problem, you still could come up with a classical model that learns this. Yeah, I mean, that's always the problem with empirical comparison. They didn't optimize over the best classical routine. Yeah. And then also basically the next result has to be taken, at least I claim, with a big grain of salt, because they did some comparison on parameter complexities there for typical classical and quantum algorithms. And they claim that for a sophisticated state encoding routine, so for this amplitude encoding, you actually can get an exponential reduction in the number of parameters you need in your network, or in quadratic reduction if you use some other type of encoding. And I mean, that's, I would say, the big hope, that you can really get this exponential reduction. Problem with this result is only that, I mean, it's really hard to prove this theoretically. And so they only did some empirical experiments there, and they did very small scale experiments, so up to I think 8, 9, 10 qubits. And so I think it's very, very difficult to really get some asymptotic behavior from that. So those are some of the prospects of quantum reinforcement learning, but so far, at least to my knowledge, there's no real proof that those scaling behaviors really hold. But still, I think some very interesting results. But what they actually can prove, and I think that's one very interesting thing, is that for some environments we really can get an exponential advantage in sampling complexity, which just means we require exponentially less interactions with the environment. Again, the downside is that it's a very constructed environment. Again, details are not too important for that. So the basic idea is that you just use a very simple classification task and then encode basically the labels with some discrete logarithm function. And as quantum computers are known to efficiently solve the discrete logarithm problem, you can show that quantum reinforcement learning agent is able to learn this environment with a polynomial amount of samples, whereas the best classical agent will always use an exponential amount of samples. So here we really have the separation. But again, this is a very constructed problem, and we are still looking for a problem that is, for example, really relevant in industry, but still I think a very important first step. And also the second downside is that the algorithm you would need for that to really run it in the real world usually requires a lot of qubits, very large systems. So that's something that we can't experimentally test nowadays. But the theory is there, so as soon basically as the quantum systems are large enough, we are pretty confident that we also can do this in practice. Yeah, so that's one of the theoretical results. And now I want to go on with some of our extensions and also actually some experiments on the actual quantum hardware. So what we did here, we took the algorithm I have just introduced and modified it. So we still, in principle, did the same thing. So we measured the quantum state in the computational basis. And so this previous raw policy just associated each basis state with one of the actions and said, I said this action here. But in the original paper, they actually didn't talk about how we should do that. So basically, which basis state should be associated with which action to also maximize the reinforcement learning policy. And to achieve that, we introduced a classical post-processing function, which should satisfy certain properties we came up with, and by ensuring that, we were able to show that you can actually drastically improve the reinforcement learning performance. But more on this later. So we post-process our results based on this post-processing function. Then the agent can just decide for an action to execute. And also in the next step, we can use the same post-processing function to also efficiently, or at least more efficiently, compute the gradients and therefore be able to perform just some gradient-based update techniques. And now just a very simple example. So what we actually want to do is we want to represent our policy in terms of this absolute squared amplitudes of our quantum system. And here we have the thing I mentioned on one of the first slides, that we actually, just physics gives us this normalization condition here. So basically the absolute squared amplitudes define some probability distribution, and also our policy is typically a probability distribution, so this is actually a very good fit. So what we could do here, we can just measure our quantum state in the computational basis, and for a 3-qubit system, this means we will get one of those 8 computational basis states. And now, for example, one possibility would just be to look at the first qubit of information and say if the first qubit is a 0, then we select action 0, and if the first qubit is a 1, then we select action 1. So that would be a perfectly viable association between basis states and actions. So we can say just something like the action should be the value of the first qubit. That's totally fine. But that's only one of many possibilities. And basically the other extreme example would be that we always consider the information of all the qubits. So we just say we do something like the parameter, the parity, so basically this XOR modulo 2 operation, and say if we have even parity, we decide for action number 0. If we have odd parity, we decide for action number 1. So those are 2 possible post-processing functions. And inherently, it's not very clear which one should we prefer. And so that's actually the question we wanted to answer in this work. So to make things a bit easier to analyze, we extracted things one step further from the quantum realm and said instead of looking at this basis states, we just want to look at the measured bit strings. So we can just say what we basically need to do, we have this 2 to the power of n bit strings and just want to group those bit strings into sets which are associated with the different actions. And then if we measure one bit string, we basically can just look in which state it is contained and then decide for an action. So that's the underlying idea. And yeah, again here we basically just did some reformulation that we are also able to estimate the policy on an infinite number of samples, because in theory to get the exact policy you would have to sample the quantum circuit infinitely many times, which is obviously not feasible. So we also show that we can basically approximate it with a finite number of samples. And even more important, for action selection, so basically for this part here, it's really sufficient to just sample the quantum circuit once. Because again, this condition here, so we directly can sample from this probability distribution. So we really just measure the quantum state once, observe the bit string, and then directly can decide which action we want to execute. So this is a really huge save compared to having to sample expectation values here. Yeah, and then we wanted to come up with a measure which basically describes how good is a certain post-processing function, so a certain association between bit strings and actions. And so the motivation for that is that we actually could associate these different associations with global and local measurements. So the first example, where we just say the action is the value of the first qubit, would just correspond to a measurement of the first qubit. This parity operation actually would correspond to a measurement on all of the qubits. So that's the underlying idea. But there are some flaws to that, because this simple consideration only works for 2 actions, and typically we look at environments with much more actions. And also the formulation is not that clear, because in quantum computing there are concepts that for some cases you can compress the information of multiple qubits into one qubit and only measure that one and guarantee the same measurement. And this is actually one of the cases, so we can introduce a helper qubit, just do some 2-qubit operations, which basically introduce some entanglement there, and just measure the single qubit, and actually the measurement on this single qubit guarantees us the same result as the measurement on this multi-qubit measurement. So the distinction between basically single qubit and multiple qubit measurements is not that clear anymore. And so we came up with some more robust routine, or a more robust definition for that, which we named extracted information. And this basically just should describe how many bits on average do we need to distinguish between the different actions. So just some simple example for that. Those are just the action associated sets we want to have. So overall we have 2 to the power 4, so 16 basis states. We have 4 actions. So basically in each class we just want to have 4 basis states. And with the basis states we measure is in that class, we decide for that action. And so if we, for example, measure the bit string 0, 1, 1, 1, in this case it's actually enough to just consider the first and the last qubit, or the first and last bit. And if we have that information, we can directly tell we want to execute action 1. And other example, if we measure this basis state, so 1, 0, 1, 1, we actually need to look at 3 qubits. So we only can omit the third qubit. So basically there's more information important in this example. And then, so it's one thing we can directly say, if we have, for example, 4 actions, we need at least a discrete logarithm of 4 equals 2 bits to decide on an action. So that's basically the lower bound. And then what we did next to give basically more expressivity to this measure, we just average over all possible bit strings. And yeah, we also can define upper bound there, which basically tells us if we just have n bits, we can't use more than n bits of information, because that's the maximum number that's available. So basically we always are in that range between logarithm or discrete logarithm of number of actions and the number of qubits. And problem a bit with this measurement here is that it's very hard to compute. So there are several exponential scaling factors. So we want to average over an exponential number of bit strings. So already that is basically infeasible to compute. and also computing the expected information for 1 qubit is already, for 1 bit string is already very hard. So this measurement is, cannot be evaluated, or at least we believe that cannot be evaluated for general setup. But the nice thing is that you can use it to construct concrete post-processing functions. So we actually came up with this function here, which also uses some parity information. So the actual setup is not too important here. But what is very important is that you can show by some induction proof that for this post-processing function, you always guarantee the maximum number of this measure. So we call it globality measure. So you basically always guarantee the maximum globality, which means that you use the maximum information that's available in our system. And to our intuition, that makes sense that we want to use as much information about our quantum state as possible. And in fact, if we run some experiments, it turns out that this seems to be true. So all these curves are tests on the cardboard environment with exactly the same quantum network, exactly the same setup. The only difference here is that we use different classical post-processing functions. And so the best performing one was this green one here. And here we actually used the post-processing function constructed basically from a theorem I have shown you on the previous slide, which guarantees us this maximum globality. And on the other end of the spectrum, we have this purple plot here. And the purple plot actually uses the least amount of information you can get away with in this setting. So only 1 bit, because we have to decide between 2 actions. And everything in between is basically ordered in ascending order of increase of this value. This gray plot here is actually the more complex softmax policy I have shown you on one of the slides. And so in the original paper, the authors actually concluded that the softmax policy is superior to the raw policy because just it's more flexible. But it turns out that if you just use a more sophisticated post-processing function, you actually can outperform it with a much simpler setup. So that are basically the main results we got from that. And yeah, we also did experiments on other environments, also more complex cardinal environments, frozen lake environments, and we always basically observe the same behavior. So if we use a more global post-processing function, then we can drastically improve the performance of our reinforcement learning agent. And one thing that is very important here is that this basically doesn't increase the complexity of our learning algorithm at all. So first of all, the quantum part is exactly the same. We use exactly the same networks, exactly the same training routine, so there's no increased complexity. The only difference is that different post-processing functions might have different complexities to evaluate. And it turns out actually some of them are require an exponential amount of data to be evaluated. But what is very nice about the construction we came up with is that for the global post-processing functions, so the one with basically the perfect globality value, you always have an efficient routine to evaluate them. So you actually don't increase the complexity of your algorithm, but you can drastically improve the performance. We also had a look at some other measures which should classify the expressivity and trainability of our model. So basically some evaluations of the Fisher information matrix corresponding to the system. And so the first one is the so-called effective dimension. And this effective dimension should classify how big is the range of functions we can represent with a given model. And it turns out that for just better post-processing functions, also the range of functions we can approximate is just much bigger. And although trainability, so basically how easy is it to find a good parameter set for our model, also here it turns out that for those more sophisticated post-processing functions, it's typically easier to also train it. So those are basically, we believe, the two main ingredients that are the reasons why this there's this big difference in using different post-processing functions there. And then finally, with this improved algorithm, we also did some experiments on actual quantum device. So I think we run this already 1.5 or 2 years ago. So we went for a very small system back then with 5 qubits. So basically back then it wasn't really able to do anything bigger. And we got those results here. So green again is just a classical simulation. So here we basically get very close to the optimal results. And then we had 2 runs on the quantum system. So orange is basically a run where we also try to correct for some of the errors. So there are some routines where we make some assumptions about the errors that might occur, and you actually can correct some of them. And blue was just without any error correction or error mitigation techniques. And I mean, you can see some difference in those two. So there was actually some improvement. But the main thing which we were very happy about is that we were able to show that the agent is actually able to train. So it might not reach the perfect performance, but it actually drastically improves upon a completely random policy. And then we actually looked at the concrete policy that it has learned. So this was some contextual bandits environment. And what we actually observed there is that in basically for all of the cases, it was able to identify the correct action. So the correct action is always marked in green. And basically we also noted the corresponding value of the policy. So in all the cases, our policy recognizes the correct action. The only problem is that the probability of selecting that action is not high enough. So basically our policy is not peaky enough. And we're pretty sure that the reason for that is just that there's a lot of noise in the quantum systems, and it's really difficult to get upon a certain level with the policy. So basically, as soon as there are any improvements to the hardware, we are pretty sure that this performance will improve. And actually, we just rerun this experiment some weeks ago, and actually observed that just by improvement of the hardware, all of those values are now closer to 90–95%. So that's really just some hardware constraint we still have. But overall, I think this demonstrates that this algorithm is also feasible for the actual quantum hardware. Of course, this is a problem where in the first place it might not make sense to use quantum computing, because this is a very simple problem. You also can do this classically. But I think you have to start somewhere, and then gradually go towards bigger and more complex problems. Yeah, so much for that first extension. And then what I also told you about in the recap is that we wanted to introduce this network gradient approaches. So we again took a very similar pipeline with the modification that now we also wanted to introduce the second order terms. And it actually turns out that for certain approximation to the second order terms, they are very efficient to compute on the quantum hardware. So that's was one of the main motivations for that. So where we come from is just again this first order gradient update with gradient ascent. And again, the problem, we don't really pay attention to the geometry of our parameter space. So very small changes in each parameter space might lead to very big changes in a policy space, which usually could lead to a very unstable training. So we want to basically introduce the second order terms. So usually in the form of the inverse of the Fisher information matrix. And so you typically sketch it as some way of undistorting your parameter space, so that basically updates have the same basic influence on the policy in each of the directions. So that's the intuition behind it. So your training should be able to converge much more smoothly. And there's also a quantum analog for that, so the Fabeni study metric, or also referred to as quantum Fisher information matrix. again, definitions are not too important here. But one big problem about that is it's very difficult to really get access to this information. To really sampling this full quantum fish information matrix usually also requires an exponential amount of samples, which is usually not feasible. But actually, just also very recently, in 2020, there was a paper which proposed an approach to efficiently sample an approximation of that information matrix, and it actually turned out that already this approximation is sufficient to get quite a good speed up in basically the reinforcement learning performance. So this is the algorithm we came up with. So we sample this approximation of this quantum fish information, compute its pseudo-inverse. Usually you do that with some quadratic optimization routines, and you also can introduce some additional regularization parameters to get things more stable. And then you basically still follow the same routine from the reinforced algorithm. The only difference is that you also include this second order terms into the update. And then finally, we've also evaluated this first of all on a very simple problem. So here we only used 1 qubit actually, and 2 trainable parameters. And we try to learn this contextual bandits environment, so 2 states, and basically in both states, the action number 0, or basically the left action, is the one you want to take. And so the reason why we went for this simple environment is that we only have those 2 parameters in our network, and therefore we can get a nice visualization of our landscape. So basically, what the agent should do, it should locate this optimum up here, because this guarantees us the optimal reward of +1. And again, this is not a very difficult problem, but it already highlights that the natural gradient will be much faster than the vanilla gradient. So we did experiments with just some random initializations in that landscape, and we observed that, I mean, all of them are able to locate the optimum as expected, but actually the natural gradient is much faster in doing so. And also, the regularized natural gradient typically is a bit slower because of this regularization term, but for some setups actually it's more stable. For example, for this setup here, so here we use a slightly different environment, which results in a different landscape. And here we can observe that the normal natural gradient has a very difficult time converging, because just the training is very unstable. But again, the regularized gradient or regularized natural gradient clearly outperformed the vanilla approach, so the first order approach. And we wanted to dig a bit deeper in why that is. So we took a look at concrete initializations, and it turns out if you, for example, initialize near the minimum, where the landscape has approximately the same gradient magnitude in all of the directions. So basically the parameter landscape is deep in both directions. Then both of them are able to converge pretty smoothly, but again, the natural gradient update is just faster. And then there are regions in our landscape which are quite distorted. So for example, the gradient in one direction is very high, and the gradient in the other direction is very close to 0. And in those regions, the vanilla, so first order update, struggles a lot, while the natural gradient update is basically able to account for the distortion and try to converge to the optimum much faster. And we think that this is the main reason why you get this big benefit with this natural gradient there. We also can take a look at the trajectories that the algorithms take, and again, all of them will eventually be able to locate the maximum up here. But again, the natural gradient, especially if you start in this distorted region, so again, the the gradients in this direction basically are very small, and gradients in this direction are very steep. Especially in such distorted regions, the natural gradient is just able to perform much more meaningful updates and thereby have a much better convergence. And yeah, one step further, but we have no proof on that, so that's just something we assume. So there's something called the Baron-Plateau problem in quantum computing or in quantum machine learning, which is closely related to vanishing gradients in neural networks. Only it's much worse, so it's much more difficult to deal with that. And actually, so natural gradients are believed to be one method to at least mitigate this problem to some extent. So that's also one potential benefit of our algorithm. Yeah, and then lastly, we also did some hardware experiments again. So those are much more recent, and we actually, for that, we used the quantum device in Eningen and used a subsystem of 12 qubits. So just as general order, up to 30 qubits is about the range where you can simulate anything things classically. If you have some HPC sender, you maybe can go up to 40 qubits, but after that, just not possible to simulate it anymore. So you're slowly approaching the region where things really get interesting because we can't do the same things classically anymore. But still not there yet, but we're going towards it. So we use 12 qubits, so this 12 qubit circuit for this example here, this contextual bandits environment, and we just compared again in classical simulation here the natural and the vanilla gradient update, and also it turns out here that the natural gradient is just faster. The difference is not that significant for this environment, but still, if you keep in mind that the basically big bottleneck for the algorithm is the computing of first order gradients, and second order gradients are very cheap. Still, I think this improvement is very good. And then we did some experiments on the hardware. So red again is a simulation, and blue is the run on the actual hardware. And again, we were able to show that our agent is able to run. Just at some point, we again hit this boundary where just the noise gets overwhelming, and we're basically never able to train above a reward of 0.6. And also, if you just took the optimal parameters, which we were able to analytically compute for this environment, we still got a reward around this range. So that's just again the current constrictions of the hardware. So we just can't go above that yet, but I'm pretty sure the hardware will also improve in the next years. And yeah, then again, just an important point, as before for the post-processing function, also integrating this natural gradient doesn't really introduce any significant complexities into your algorithm, but it usually improves the performance. So just as a broad overview, what we have learned today. So we combined basically the two topics of reinforcement learning, deep reinforcement learning, and quantum computing, and took a look at different quantum reinforcement learning algorithms. We started with the, let's call it vanilla policy gradient or quantum policy gradient, where we just replaced the neural network with a variational quantum circuit. Then we took a look at classical post-processing of our measurements, which improves the reinforcement learning performance. And on the last slides, we improved even further upon this by introducing second order gradients into our update routine. Yeah, so this concludes my talk to today. And if you are interested in the topic, I also composed some list of further references here. And with that, thanks a lot for coming, and thanks a lot for your attention. Yeah, if there are any questions, I'm also happy to answer it. Let's see you on Friday.